Hello everyone, welcome to EPG Pathshala. Thank you for having me here. My name is Dr. Saif Saeed. I am Assistant Professor in Jamia Millia Islamia University, New Delhi. I am going to be speaking to you about the module which is entitled as Remote Sensing Systems, Platforms and Sensors. This module is divided into 6 major headings that includes an introduction part followed by historical development of remote sensing, history of India's space program and history of international space program will also be looked at. Then we will move on to the topic platforms and sensors, covering classification of sensors as well as satellite characteristics such as orbits and swaths. Finally, weather and communication satellites will also be covered in this module. At the end of this module, student will be able to briefly explain historical evolution of remote sensing and detailed information related to India's space program. The two important types of satellite orbits which are required for obtaining a full image coverage of the Earth, classification of sensors, active and passive remote sensing sensors, the essential features of various important weather and communication satellites. So, let us start with the general introduction about remote sensing. The underlying principle as well as the basic concepts of remote sensing that are required for understanding the process involved in the technology have been explained in detail in the previous module, which is the fundamentals of remote sensing. The electromagnetic energy emitted from the sun or reflected back from the target is recorded by the sensors that may be mounted on the truck or on board aircraft or space satellite. The sensor platform combination determines the characteristics of resulting data or image. Henceforth, the resulting data is utilized for interpretation about the surface feature characteristics. The following module takes a closer look at the sensor and sensing platform combinations as well as the type of data collected by different sensors. This module also addresses on the historical developments and evolution in remote sensing technology in context to Indian space missions as well as foreign space missions. Let us now throw some light on the historical development of remote sensing. The evolution of remote sensing technology started way back to more than 120 years with the invention of primitive camera capable of capturing still photographs on the earth. Towards mid 1800s, looking down the earth's surface from higher altitude triggered installation of camera on hot air balloons so as to capture perspective pictures of the ground surface that aided in the preparation of topographic and navigational maps. The most novel platform for camera installation in the early 19th century was the pigeon fleet that operated as a novelty in Europe. Figure number 1 illustrates the primitive camera installed on the pigeon. During the First World War, cameras were installed on aircrafts that provided perspective photographs of fairly large ground areas that proved to be fruitful during military reconnaissance and operations. Since then, aerial photographs were primarily being used for observing the Earth's surface from the vertical or oblique perspective, which is illustrated in figure number 2. It was after World War II that aerial photographs were made available for civilian use, and the applications were mainly focused on geology, forestry, agriculture, land use, practice and topography. Figure number 2 illustrates cameras installed on airplanes in the early 1900s. During the early 1940s, both Russia and America started their space missions to image land surfaces using several types of sensors installed on board spacecrafts. Cameras were attached to V-2 rockets that were launched in 1946 after World War II to high altitudes. With the advancements, towards more extensive space program in mid-1960s, Earth orbiting cosmonauts and astronauts required photographs of Earth and Moon from their spacecraft. The world's first artificial satellite, Sputnik 1, was launched on 4th October 1957 by Soviet Union. Since then, improvements in sensor configuration on board various Earth observing satellites such as Landsat, Nimbus, and more recent missions such as RadarSat and UARS provided global images in different regions of electromagnetic spectrum, which proved to be useful for various civil, research and military purposes. Research groups in NASA Research Center developed Fourier transform techniques that enabled notable enhancement of satellite data. With the improvements in the availability of satellite images, integrated with image processing tools has led to numerous applications of remote sensing in various domains. Now, moving on to the history and development of India's space program. Although Indian scientists before independence had confined knowledge about the rocket science and space technology, since the technology was being used during world wars. It was only after India achieved independence, the process of exploring the space actually accelerated. Dr. Vikram Sarabhai founded the Physical Research Laboratory, which is also abbreviated as PRL, in Ahmedabad on November 11, 1947, that proved to be the first step that India took towards becoming one of the leading space power. It was in 1969 the Indian Space Research Organization ISRO was established. The establishment of ISRO institutionalized the space activities of India and is managed by the Department of Space, which reports to the Prime Minister of India. India's first major success was achieved on April 19, 1975 with the launch of indigenous satellite named as Aryabhatta into space. It was launched by the Soviet Union using Cosmos 3M launch vehicle. India has launched more than 100 indigenous satellites as of January 2017, offering a number of applications since its first launch in 1975. A series of satellites that have been launched includes the Apple in 1981, Bhaskara 1 1979, Bhaskara 2 1981, INSAT 1 series which includes 1A, 1B, 1C and 1D, INSAT 2 series, that is 2A, 2B, 2C and 2D series, IRS, which is Indian Remote Sensing Satellite series, which includes 1A, 1B, 1E, P2, C1, P3, 1D, P6 and Rohini 1A, 1B, 2 and 3 to name a few. India has also developed various launch vehicles that makes space program independent and are the most important technological measure of its advancements. Prominent among them are Satellite Launch Vehicle SLV, Augmented Satellite Launch Vehicle ASLV, Polar Satellite Launch Vehicle PSLV and Geosynchronous Satellite Launch Vehicle GSLV. Also, let's discuss briefly the history of International Space Program. There had been numerous celestial studies carried out from the Earth using optical telescopes until Second World War that reckoned the development of powerful rockets capable of direct space exploration. The first artificial satellite, Sputnik 1, was launched by USSR, which is now Russia, on October 4, 1957, followed by Explorer 1, the first satellite which was launched by United States in the year 1958. The first moon landing by the American Apollo 11 spacecraft in the year 1969 is often considered as landmark of initial space exploration period. The Soviet space program achieved many milestones, including the first living being in the orbit in 1957, the first human space flight, Yuri Gagarin, aboard Vostok 1 in 1961, the first spacewalk by Elie Kisilinov in 1965, the first automatic landing on another celestial body in 1966, and the launch of the first space station, Salyut 1 in 1971. Since then, countries, namely People's Republic of China, European Union, Russia, Japan, Canada, United States, France, and India have initiated successful space missions by launching multitude of satellites for defense as well as research purposes. Now we move on to the main theme of the module, that is platforms and sensors. A device capable of measuring and recording the electromagnetic energy is referred to as a sensor. For a sensor to collect and record electromagnetic energy reflected or emitted from the target or feature space of interest, it must be installed on a stable platform that may either be ground based, aircraft or balloon based, or it may be a spacecraft or satellite above the Earth's atmosphere. Now, sensors installed on ground based platforms records detailed information about the feature or surface area such as crop field or road intersection of limited extent, that is 200 to 400 square meter, which may be compared with the information collected from spacecraft or satellite sensors as per the requirements of the researcher. In some cases, data collected from the ground based sensors can also be utilized to characterize and interpret the target feature that is also being imaged by other sensors, thereby integrating the information in the imagery for better analysis. Sensors may be installed or mounted on ladder, tall buildings, cranes, etc., and the figure is illustrated in figure number 4. Now, sensors that are mounted on air-based platforms. Airborne platforms are employed owing to their mobilization, flexibility, and capability of recording data covering large spatial areas as compared to the ground-based sensors. The speed, altitude, as well as orientation of the aircraft must be carefully chosen so as to have minimum influence on the scale, resolution, and geometric characteristics of the recorded images. Airborne remote sensing is deployed when the study areas are inaccessible for ground-based platforms such as hilly regions or dense forest cover. Remote sensing aircrafts can be of many types. That is, they are very small in size, slow, and very low flying to twin engine turbo propeller based, which is again illustrated in figure number 5. And also small jets which are capable of flying at very high altitudes are also used as platforms for installing the sensors. Figure number 5 illustrates aircrafts used as platform to record the data pertaining to Earth surface. Sensors mounted on space-based platforms. Space-borne remote sensing is carried out from the outer space or at an altitude higher than the Earth's atmosphere and utilizes space shuttle or more commonly satellites as platforms. Satellites are man-made objects that revolve around the Earth, and sensors installed on board captures data of the Earth's surface covering areas of more than hundreds of square kilometers. Because of their orbits, satellites permit repetitive coverage of the Earth's surface on a continuing basis. Ever since the launch of the first Earth resources satellite, that is Landsat, in 1972, satellite-based remote sensing has continuously served towards the betterment of science and technology. Figure 6 illustrates space-based sensor mounted on space shuttle. Different types of orbits are required to achieve continuous monitoring for the purpose of meteorology, global mapping, that is land cover mapping, or selective imaging, for example, urban areas or some other areas. The following orbit types are more common for remote sensing missions. Polar orbit. It has an inclination angle between 80 degrees and 100 degrees that confines the satellite motion in westward direction. Polar orbit enables observation of the whole globe, including the poles. Satellites with polar orbit are launched at 600 km to 1000 km altitude. Sun synchronous orbit, also referred to as near polar orbit, having inclination angles between 98 degrees and 99 degrees, which is relative to a line running between north and south poles, thereby enabling satellite to always overpass overhead at the same time. Most sun synchronous orbits crosses the equator at mid-morning at around 10:30 hours local sun time. Examples of sun synchronous satellites are Landsat, IRS and SPOT. The third type of orbit is the geostationary orbit, which has 0 degrees inclination angle. That is, satellite is placed above the equator at an altitude of 36,000 kilometers. The orbital period is kept equal to the rotational period of the Earth that results in fixed position of the satellite relative to the Earth. That is, satellite observes and collects information continuously over specific areas and always views the same portion of the Earth. Due to their high altitude, geostationary weather satellites monitors weather and cloud patterns covering an entire hemisphere of the Earth. Geostationary orbits are commonly used for meteorological and telecommunication satellites. The above section is followed by the classification of sensors. Sensors are the devices which are used to record the electromagnetic radiations emitted or reflected from the target features and acquire images used in the variety of remote sensing applications. Sensors are broadly classified into three categories: optical sensor, microwave sensor and the thermal sensor. Optical sensors. Optical sensor utilizes the energy from sun, which is the source of illumination, by recording the energy reflected or emitted from the target feature. Optical sensor record the reflected or emitted energy in the visible, near infrared and short wave infrared regions of the electromagnetic spectrum. Optical sensors are sensitive mainly to the electromagnetic radiations lying in the range of 0.4 micrometers to 0.76 micrometer, which is the visible region of the electromagnetic spectrum, as well as 0.76 micrometer to 0.9 micrometer, which covers the near and mid infrared band. The wavelengths which are insensitive to human eyes are captured. Images acquired from optical sensors finds usefulness in the variety of applications such as post-earthquake damage assessment, landslide damage assessment, oil spills, vegetation monitoring, flood assessment and relief measures, land use and land cover classification, temporal change detection analysis and many more. Optical remote sensing systems are classified into three types: panchromatic imaging system, which is often referred to as PAN or PAN images, multispectral imaging system and hyperspectral imaging system, depending on the number of spectral bands used in the imaging process. We move on to the panchromatic imaging system, which is often referred to as the PAN image or PAN images. The imaging sensor is a single channel detector sensitive to wide range of wavelengths of light typically covering the entire or large portion of visible band of the spectrum, thus resulting in gray scaled image, that is, images containing different shades of black and white. Examples of panchromatic imaging system are Iconos pan, spot pan, IRS pan, quick bird pan, just to name a few. Figure 7 refers to the panchromatic image extracted from spot pan sensors with ground resolution of 10 meters. Now, multispectral imaging system. The multispectral scanner or MSS is one of the important Earth observing sensors introduced in the Landsat series of satellites that uses an oscillating mirror to continuously scan the Earth's surface perpendicular to the spacecraft velocity. The resulting image is a multi-layer image which contains both brightness and spectral, that is color, information of the targets being recorded. Some of the examples of multispectral systems are Landsat MSS or multispectral scanner, IRS LIS, LISS, Spot XS, Iconos MS. The multispectral scanners are further divided into following two types: whisk broom scanners and push broom scanners. Whisk broom scanners, this type of scanner is an optical mechanical device which is also known as a cross track scanner. This scanner uses a rotating mirror and a single detector which scans the scene along a long and narrow band. The orientation of the mirror is such that on completing one rotation, the detector scans across the field of view between 90 degrees and 120 degrees to obtain images in narrow spectral bands ranging from visible to mid-infrared regions of the spectrum. Figure number 9 depicts the scanning mechanism of whisk broom scanners. Now, the second categorization of the multispectral imaging system is the push broom scanners. These are also termed as along track scanners and does not have a mirror looking off at varying angles. Instead, there is a line of small sensitive detectors stacked side by side, each having tiny dimension on its plate surface. These may be several thousand in numbers, and each detector is a charged coupled device, that is, it is a CCD. In other words, these scanners consist of a number of detectors equivalent to the swath of the sensor divided by the size of the spatial resolution or pixel size, which is very well illustrated in figure number 9b. Now, the third category or third characterization of the imaging system is the hyperspectral imaging system. Hyperspectral sensors are also referred to as imaging spectrometers that acquire images in very narrow and large number of contiguous spectral bands, that is, typically collect 200 or more bands of data throughout the visible, near infrared, mid infrared and thermal infrared regions of the electromagnetic spectrum. This is again illustrated in figure 10. A Landsat thematic mapper records an integrated response from the data point in 7 spectral bands of approximately 0.26 micrometer wide, whereas the hyperspectral scanner records the spectral response of the same point in a large number of bands in the order of 0.01 micrometers. Now, the third characterization of the sensors is the microwave sensors. The microwave region of electromagnetic spectrum extends from wavelength approximately 1 centimeter to 1 meter. The longer wavelength have spatial characteristics of penetrating the cloud cover, heavy precipitation, haze or dust, and are not susceptible to atmospheric scattering, which otherwise shorter optical wavelengths are prone to be scattered. These properties allows microwave remote sensing in almost all weather and environmental conditions and at any duration of time, even during the night time. The sensors operating in the microwave regions are broadly classified as active and passive sensors. Now, passive sensor records the intensity of microwave radiation ranging between a frequency range of 5 to 100 gigahertz emanating from the surface of the earth within the antenna's field of view. The passive sensors that measure the emitted energy are the microwave radiometers. The microwave energy recorded by passive sensors is quite low as compared to the optical wavelengths since the wavelengths are so long, and therefore, the field of view of the antenna is kept large to record sufficient energy. Most microwave sensors are therefore characterized by low spatial resolution. The important application of passive microwave remote sensing include areas such as hydrology, oceanography and meteorology. Figure 11 depicts microwave energy recorded by a passive sensor, or it also illustrates the working principle of passive microwave remote sensors, which records the energy emitted by the atmosphere, that is capital A, it is symbolized by capital A, reflected from the terrain features symbolized as capital B, emitted from surface features symbolized by symbol C, or transmitted from the subsurface, which is symbolized by letter capital D. An active remote sensor emits their own electromagnetic energy in the microwave region towards the surface feature, which after interaction with the target produces a backscatter of energy, which is finally recorded by the active sensor's receiver. This phenomena or this mechanism or working principle of active microwave remote sensing is illustrated in figure number 12. Active microwave sensors are further categorized into imaging and non-imaging category. The most common form of imaging active microwave sensors is radar, which is also an acronym for radio detection and ranging altimeters, and scatterometer comes under non-imaging microwave sensors category. The most widely used active remote sensing systems is the radar, which transmits long wavelength microwave radiations from 3 centimeters to 25 centimeters and records the reflected energy from the target feature in the form of backscatter. Figure 12 depicts the working principle of the active microwave sensor. The microwave region of the spectrum, which is again depicted in figure number 15, is quite large in contrast to the visible and infrared and broad classification of the several wavelength ranges or bands commonly used are mentioned below. X band, which is used extensively for military reconnaissance and terrain mapping. C band, sensor on board NASA spaceborne systems include NVSat, ERS-1 and 2 and RadarSat, mainly used for surface soil moisture mapping. S band sensor on board Russian Almaz satellite and used for biomass modeling. L band, the sensors are installed on board American CSAT and Japanese JERS-1 satellites and used for subsurface explorations. There is a P band sensor which is on board NASA airborne research systems. Again, it is used for archaeological explorations. Now, the last category of or categorization of the sensors is the thermal sensors. All objects selectively absorb short wavelength solar energy and radiate thermal infrared energy. Objects having temperature above absolute 0 or 0 Kelvin starts emitting electromagnetic energy in wavelength range between 3 micrometer to 100 micrometer. In a thermal image, the tone of an object is a function of its surface temperature and its emissivity. That is, all objects emit infrared radiation and the amount of emitted radiation is a function of surface temperature. In short, hot objects appear in lighter tone and cooler objects appear darker tone in an infrared image. Some of the applications of infrared thermal remote sensing can be broadly classified into two categories. One, in which surface temperature is governed by man-made sources of heat, and the other, which is governed by solar radiation. In the former case, the technique has been used from airborne platforms for determining heat losses from buildings and other engineering structures. In the latter case, thermal infrared remote sensing has been used for identifying crop types, surface soil moisture monitoring, forest fires, military operations, as well as identification of crop species for detecting crop diseases. Now, let us take a look into satellite characteristics, that is orbits and swaths. The path followed by satellite is referred to as its orbit. Satellites are launched into the desired orbits based on the onboard sensor capabilities as well as the objectives of the launch mission. Currently, more than a dozen orbiting satellites provides variety of data that plays significant role in enhancing the knowledge of the Earth's atmosphere, oceans, glaciers and land. Selection of satellite orbit takes into account the altitude, that is the height above the Earth's surface, and sensor orientation as well as its movement relative to the Earth. Satellites at very high altitudes which view the same portion of the Earth's surface at all times have geostationary orbits. It is again shown in figure number 17a and also discussed in the earlier sections. Weather and communication satellites are commonly have geostationary type of orbits due to their high altitude. Some geostationary weather satellites can monitor weather and cloud patterns covering an entire hemisphere of the Earth. Figure 17a depicts the geostationary satellite, 17b depicts the polar orbiting satellites. Sun synchronous or polar orbiting satellites have inclination of the orbit relative to a line running between the north and south poles as shown in figure 17b, covering each area of the world at roughly the same local time each day. Landsat satellites and IRS satellites are the typical examples of sun synchronous or near polar satellites. The satellite, while revolving around the Earth, scans a certain portion of the land area, and the width of the area scanned during a single pass is called as the swath. The swath is illustrated in figure number 20. Swath widths for space-borne sensors generally vary between tens and hundreds of kilometers wide. For example, swath width of the IRS-1C LIS-3 sensor is 141 kilometers in the visible bands and 148 kilometers in the shortwave infrared band. Any communication that makes the use of man-made satellites in its propagation path is referred to as the satellite communication and plays a dominant role towards advancement in technology for betterment of the mankind. There are numerous artificial satellites in operation employed for traditional point-to-point communications, mobile applications and the TV broadcasting and radio programs. Satellite communications uses high frequency signals such as ultra high frequency UHF ranging from 300 megahertz to 3 gigahertz and super high frequency SHF ranging from 3 gigahertz to 30 gigahertz. Satellites that are primarily used to monitor the weather and climate of the Earth are referred to as weather satellites. These satellites can be polar orbiting, scanning the entire globe in successive passes, or geostationary over the same spot over the equator. There are several geostationary meteorological satellites in operation such as GEOS 12, GEOS 13, GEOS 15 of United States, Electro L1, Russia's new generation weather satellite. The INSAT series of satellite carries very high resolution radiometer, that is VHRR, for providing data for generating cloud motion vectors, cloud temperature, water vapor content utilized in the modeling and forecasting of rainfall, movement of thunderstorms and cyclones. ISRO has also designed and developed ground-based observation systems such as Automated Weather Station AWS, Agrometeorological or Agromet Tower and Doppler Weather Radar DWR to augment the space-based observations and validating the events directly associated with the various natural phenomena. With this, we conclude this module and thank you very much for your kind attention.